Hello everyone, I am MD Rafiul Ratul from Department of Electrical and Electronic Engineering at American International University of Bangladesh. Today I am presenting my research work which title is MedLink WPT, a resonant four-coil wireless power transfer system for battery independent capsule endoscopy. The central idea is to deliver power safely through biological tissue without relying only on an onboard capsule battery. I will focus on the design, tissue-loaded simulation, performance results, and electromagnetic safety validations. The presentation roadmap. The presentation begins with in the motivations, battery limitation in conventional wireless capsule endoscopy. Then I will introduce the proposed four-coil resonant WPT link and the main research objectives. After that, I will cover the coil model, tissue phantom setup, and the key CST simulation results. Finally, I will discuss SAR safety, limitation, and optimization pathways and the conclusions. Core problem: battery limited capsules. Wireless capsule endoscopy is clinically useful, but its operation is strongly considered by the onboard battery. A typical battery lifetime of about 8 to 12 hours can limit full transit diagnostic coverage. The battery also consumes valuable capsule volume that could otherwise support imaging, sensing, or communication modules. Therefore, a battery independent powering method is important for longer, safer, and more capable capsule operation. Proposed solution: MedLink WPT. To address this limitation, we propose a resonant four-coil wireless power transfer architecture. The external side contains the source and the transmitter coils, while the internal capsule side contains the receiver and load coil. The system operates at 12.979 MHz and it's designed to transfer power through uh, abdominal tissue. All electromagnetic performance evaluations were conducted using CST Studio Suite 2019. The research objectives. The first objective is to design a compact four-coil WPT structure suitable for capsule size integration. The second objective is to evaluate its tissue-loaded performance using a multi-layer abdominal phantom. The third objective is to analyze matching, coupling, Q-factor, efficiency, field distribution, and loss behavior. Finally, the work verifies electromagnetic uh, exposure safety using SAR analysis. Key contributions. This work contributes a compact source transmitter receiver load coil arrangement for battery-free capsule endoscopy. The receiver side coils are um, miniaturized to improve capability use with capsule scale constraints. A CST full wave simulation is performed through a realistic multi-layer abdominal tissue model. A study reports S parameter, BSWR, and power transfer indicator and SAR safety result in one integrated framework. Distinction of the proposed work. The novelty is not that wireless power transfer itself is new. Rather, the contribution is the combined system level design and safety evaluation. Compared with a simpler two-coil arrangement, this study uses a four-coil resonant configuration to improve design flexibility. The simulation is tissue-loaded instead of being limited to free space assumptions. This makes the work a safety-focused proof of compact for deep tissue capsule powering. Four-Coil WPT system architecture. This architecture can be read from left to right, starting from the RF source outside the body. The transmitter coil strengthens the alternating magnetic field and couples energy across the tissue path. Inside the capsule, the receiver coil captures the field and transfer power to the load coil. The separation of external and internal resonance supports both stronger external excitation and compact capsule integration. Coil geometry, dimensions, and trans. The geometry shows a clear size difference between the external and internal coil sections, and the transmitter coil is intentionally larger with a 76 millimeter outer diameter to create stronger magnetic coupling from outside the body. The receiver and the load coils are much smaller with diameters suitable for capsule side integration. The size trades off improves practically, but it also makes transmitter to receive coupling more challenging. Coil electrical parameters. The electrical parameter defines how the resonant behavior is achieved at 12.979 MHz. The transmitter and receiver coil use turning capacitance, while the source and the load coil mainly acts as coupling coils. Inductance, capacitance, and resistance together determine resonance, loss, and bandwidth. The receiver side um, miniaturization are practical for capsules, but it increases resistance-related limitations. Coupling coefficient. The coupling coefficient indicates how strongly two coils are magnetically linked. The source to transmitter coupling is moderate, while the transmitter to receiver coupling is weak at 0.0275. This weak TX to RX coupling is expected because the tissue distance and the smaller receiver and coil diameter. However, the receiver to load coupling is very strong at 0.9994, supporting compact powering deliver inside the capsule. Quality factor. The quality factor describes how efficiently a coil stores resonant energy relative to its loss. The transmitter coil shows the highest Q factor, which power supports strong resonant field generation externally. The receive and the load coil have lower Q factor because of miniaturized geometry and resonant constraints. This result identifies coil refinement and independence matching as key future optimization needs. Efficiency and power metrics. Three power metrics are used to interpret a system performance: PRR, PTR, and PTE. PRR represent reflected power. So, a lower value indicates better input power utilization. The PTR and PTE represent the delivered and effective transferred power through the resonant link. In this proof of concept, safety and feasibility are demonstrated first, while efficiency is targeted for future improvement. Multilayer abdominal phantom. The tissue phantom indicates skin, fat, muscles, and gastric walls layers to approximate abdominal propagation condition. Its tissue is modeled using a relative permittivity, conductivity, and density at the operating frequency. Permittivity affects field distribution, conductivity affects electromagnetic loss, and density is required for SAR computations. The tissue loaded setup gives a more realistic evaluation than a free space simulation. Test parameters, simulated response. The S parameters curve show the resonant response of the proposed WPT link at 12.979 MHz. At resonance, S11 is minus 13.6.6 decibel and S22 is minus 13.751 decibel, indicating acceptable input and output matching. The forward transmission S21 is minus 13.658 decibel, confirming power transfer through the tissue loaded link. These values show feasibility, and although the stronger transmission is still required for practical deployment. VSW result. The VSW result provide another view of the port matching quality. The port 1 has a VSWR of 1.5275 and the port 2 has a VSWR of 1.5171. Both values are below the common 2:1 acceptance threshold, so the matching is acceptable. However, the ideal value is 1.1, meaning further impedance matching can still improve the design. Magnetic field distribution. The magnetic field distribution confirms that the resonant field is concentrated between the external transmitter and internal receiver region. The reported maximum is field amplitude is approximately 10 ampere per meter around the coil region. This supports the intended near field magnetic coupling mechanism through the tissue phantom. The field pattern also helps identify where alignment of coil geometry optimization would be most effective. SAR safety results. This is the key safety result of the study because SAR quantifies the electromagnetic energy absorption in tissue. The maximum 1 gram average SAR is 0.688823 watt per kg, and the maximum 10 gram average SR is 1.547353 watt per kg. Both values remain below the 2.0 watt per kg localized, the exposure limit used for safety comparison. However, under the simulation condition, the proposed system satisfies the required SAR safety constraint. The optimization pathway. The current design demonstrates feasibility and efficiency needs the further improvement before practical implementations. The main optimization route includes coil geometry, refinement, better conductor design, and improve the impedance matching network. Adaptive frequency tuning and alignment our transmitter design can also help compensate for capsule movement inside the body. Future optimization must improve the PTE while keeping SAR below the exposure safety limit. Conclusion and outcomes. In conclusion, the work design and the simulation a compact four-coil WPT system and a battery-less capsule endoscopy. The system operates at 12.979 MHz and achieves acceptable matching through tissue loaded CST simulation. The reported PTE of 4.7% confirmed feasibility, although efficiency enhancement remain necessity. Most importantly, the SAR result remain below the safety limit, supporting the design as a safety validity proof of the concept. And these are all the reference. And thank you for your attention. This study a compact and safety aware WPT pathway for future battery independent capsule endoscopy. I welcome your question, suggestion, and especially on coil optimization, alignment, robustness, and experimental validation. It would be happy to discuss how this proof of the concept can be extended towards for practical prototype. Thank you.